All right, in this one we'll talk about Python's type system and control flow in Python, including parallelism. So, contrary to what some people have been saying, Python has a pretty strong type system. It's dynamic, but everything's an object. And it's hard to step on an undefined region of memory in Python. You can do it, but you have to go out of your way to do it. It's much less likely to happen accidentally than in, say, C or C++. And when I say pretty strong typing in Python, I mean that there are few implicit type conversions. The exceptions are primarily that a bool might be implicitly promoted to an int might be implicitly promoted to a float, which is a little bit strange because IEEE floating point hardware, which is how Python represents floats, they're really C doubles. They can't represent as large numbers as Python ints. Python ints can get quite huge. And the biggest exception to Python having a strong type system is that almost any data type in Python can be used in a Boolean context. We'll see an example of this shortly. But the concept of truthiness comes into play here. If you use a data type, if you use an instance of a data type as a Boolean expression, it'll be examined using dunder bool, and failing that using dunder len. Examples are int used in a Boolean context will be truthy if it's non-zero. A string will be considered truthy if it's not the empty string. Collection types, this is particularly where the dunder bool and dunder non, or sorry, not dunder non-zero, that was Python 2. Dunder len comes in. These are truthy if they're not empty. And a float you can kind of do a truthiness test of. But of course, floats are IEEE floating point hardware. So, you don't want to compare two floats for precise matching. They're imprecise. It's better to compare them within some tolerance, within some absolute magnitude being less than 0. So you probably don't want to use a float in a Boolean context, even though you can. But an example of a place where Python's type system is stronger than, say, Java's is that you cannot add a string to an integer without an explicit conversion. Here's an example of what I mean by truthiness. We're creating a dictionary with a single key value pair, and then we use that dict as though it were a Boolean. We're using it in a Boolean context. It's considered truthy if the dictionary is not empty. So this will always print was true because the dict acts like a Boolean true. That means that it's truthy. Here's some explicit type conversion examples in Python. Typically, if you want to convert a variable x to a type t and associate label y with it, you simply say y equals t of x. And here we're, in the first example, we're converting the string quote one quote to an integer, the integer 5 to a float, the floating point value 0.11111 to the end of double hardware precision to a string. We're converting a floating point value, because 1 over 9 is a float, to a string. And in the last example, we're converting a list containing simply 1, 2, and 3 to a tuple, which is basically a read-only list. Python has something sort of like type declarations. They're defined in PEPs 484 and 526. You don't have to use them. Your code today pretty much won't run faster if you do include them, unless you're in Python. I'm talking mostly about CPython and PyPy and MicroPython and things like that here. Python is kind of a different thing. Anyway, they're very optional and they're kind of a big topic. They're probably a topic for another presentation. But basically, you say a colon type equals 1, and then a will be declared to be of type, and it will get the value 1. And you can use a static analyzer like MyPy to check those things. And it's a gradual type system, meaning you can sprinkle in types as much as you want, or you can tell PyPy complain if anything isn't declared and can't be inferred. Python is a pretty good language in the sense that it's a relatively small language, but it's very extensible. A good language is small, like Lua, with a good extensibility facility. Yeah, so Python does that. Example of using a module. Here's a module that someone else has written for us. The decimal module, it's another arithmetic type, kind of like integers or floats. We'll talk a little bit about when you'd want to use it in the next slide, but here we're just creating a decimal that represents the integer value 6, or a decimal value that represents the float 0.33. Actually, it's the string 0.33. You can't normally convert directly from float to decimal for precision issues, for precision reasons. And you can multiply, add, subtract, and divide pretty much the way you would expect with a decimal. Decimals, again, are somewhat similar to floats. They're stored in base 10 rather than floats base 2, which is good when you're doing things like an accounting application where rounding errors are unacceptable. They're slower than float. They aren't done with floating point hardware in a modern CPU. And they're, well, yeah. Python is often referred to as a batteries included language, meaning it has a large, useful standard library. That's eroding a little bit. Increasingly, people just put useful code on PyPy, PyPI. But Python continues to have a pretty useful standard library that comes with it. Something like IronPython, of course, doesn't have much of a standard library, or rather, it doesn't have the standard library all in lowercase, but it does have the .NET runtime and the .NET libraries. Some people are saying that the Python standard library is where good modules go to die. And that's because Python, CPython especially, tends to not get updated that often. And of course, once a module finds its way into the Python standard library, it has to slow down its updates to that cadence. Python is very discoverable. If you want to learn more about some module or type or data instance, some instance of a type, you can simply go into a Python REPL or read evaluate print loop. Like in this example, we're running Python 3 at a shell prompt. And then we get the 3 chevrons for CPython prompt. And we import decimal, and then we help of decimal. And that help of decimal is going to look up some inline documentation of the decimal module and display it. And dir of decimal is going to report all the data and code at the top level of the decimal module. You can also apply it to say decimal dot decimal with a capital D. You can also apply these things to instances of decimal. Just an example. There's nothing special about decimal here. And you include these things by setting up docstrings. We'll talk about docstrings more later. Moving on to Python control flow. This is a example if statement. Of course, 1 always equals 1, so we print expression was true. And we know when to stop including things under the if 1 equals 1 by the dedent. This is known as the offsides rule sometimes. And of course, print done with if is always printed whether 1 equals 1 or not. Here's an if else. No big surprises here. Here's an if else, sometimes called a if ladder. And we're just comparing x to see if it's within various ranges and then printing something corresponding. Python, at least at this time, has no case statement or switch statement. Instead, most developers use if else. That is, of course, not as fast as using a case statement or switch statement in some other language. If you need the performance, that is, if you write your code and it works and you find that you need a performance boost, and it's probably best to determine that by profiling. But if you do find that you need a performance boost, you can use a dictionary of key value pairs where the keys are things you want to match on and the values are callables that you can call. I'm not going to give an example here, but they're pretty easy to find on the internet if you Google for them. And it's more clear usually just use if else. Here's an example while statement. Not much different from the if statement, really. Yeah. Here's a for loop. Here, for is going to tell range to generate the values from 0 to 4 and print each one in turn. And that range, as we discussed previously, is lazy. So it's going to return, it's going to spit out first 0, and then 1, and then 2, and then 3, and then 4. And the for I will take on each of those values in turn. It will not build a list with 0 through 4 in it before starting the for loop. This can be used with other kinds of iterators and generators. Exceptions are with try and except. You can have multiple excepts for a given try. You can also have a finally for a try, which will be executed irrespective of whether anything was caught or not caught. In this example, we're simply getting the first value from the command line and converting it to an integer and then attempting to do integer division because of the // where we're taking the reciprocal of that value we got from the command line. And of course, if the value we got from the command line was 0, then we get a 0 division error raised and we print no reciprocal. This is one of the few areas where there's something in Java I kind of envy. I wish Python had it. I kind of wish that Python would complain when you don't catch exceptions that could be raised. But of course, that's more of a implementation issue than a language issue. For else is kind of a novel feature in Python that's pretty useful. In this example, we're just going to iterate over the values from 0 to 9 one at a time. And then we compare those values with a random integer from 5 to 9. And if that random integer that we're comparing is greater than I, then we break. And if we never break out of the for loop, then the else clause is executed. So it cuts down on Boolean flags. And it's more concise. It's more clear than using Boolean flags. There's also a while else, and we already talked about try except else, I think. Try except else is just the else is just going to fire if nothing was caught. Here's an example of a user-defined function. We're simply squaring our input. No big surprises here. Here's an example of creating your own module. You could, for example, create a file foo.py and put it on your sys.path. Your sys.path being a variable that's defined in the sys module that contains a list of directories that are scanned for .py files and other code that's importable by Python. But the pure Python stuff tends to be foo.py. And if you simply define one callable, one function in foo.py say hi, then in some other code you can import foo and foo.say hi. Here is a generator example. Generators are pretty cool. They're lexically not that different from a function, but semantically they're pretty useful. Here, my range, we're simply going to generate the values from 0 to n minus 1, one at a time. So if in the example we're going from 0 to 2, so we generate 0, then 1, then 2. The key thing to notice about the yield instead of return, that's what makes it a generator, is that when that value was spit out, when the first value, the 0, is spit out, the runtime is going to keep track of where we last executed in this generator and resume on the statement immediately following that. So in this case, we'll go back up to the top of the while and resume there. And then yield 1, go back up to the while, yield 2, go back up to the while, and finally return. In Python, parallelism is kind of interesting. CPython and PyPy have rather poor threading. They do quite well, actually, threading with, at least CPython does, not certain about PyPy. CPython does quite well with threading as long as all of your threads are IO bound. But if you have a workload that is all CPU bound, CPython's threads are very bad. And if you have a workload which is, say, 100 IO bound threads and one CPU bound thread, it's still pretty bad. Now, CPython and PyPy are good at something called multiprocessing, which fakes threading using multiple processes and shared memory. It's not as fast as threading, but it's more loosely coupled, so it tends to be less bug prone. Now, this is not a language issue, but an implementation issue. There have been numerous attempts to remove CPython's GIL, the global interpreter lock, which is responsible for the poor threading. But in one case, when it was removed, when the GIL was removed, scalar code, non-parallel code, was so much slower that it was seen as not worth it. Also, other Python implementations like Jython and IronPython can thread well. So even though they're implementations of essentially the same language, they thread well because they have runtimes that are happy with threading. And CPython also has something called greenlets, which is it's concurrent within a single process. It's a good way of doing a lot of sockets in the same process. And it doesn't look like parallel code, but it really is. Or at least it's concurrent code. Maybe I shouldn't say that it's parallel code because it only happens within a single process unless you make special arrangements to have multiple processes doing the same thing. There's another way of doing concurrency in Python that's pretty nice. It abstracts away the differences between threading and multiprocessing. It's called concurrent.futures, and it makes it, if you write your code a little bit carefully, so that you can switch between threads and processes with a single line change. And here's a URL to an example program that just runs n shell commands m at a time in Python. And that's it for now. Thanks.